So welcome to Friday of week 3, Math 25. We're doing personal finance decisions. And as I briefly mentioned, we'll talk about typicality, because once we get to money issues of mortgages and saving for retirement, we'll want to say, well, the typical family would want this kind of house or this kind of retirement plan. And so we want to understand what we mean by typical more. We'll also talk about bell curves, because that's part of what typical things are being measured with, and they're important in real life. And there we go. At the end, there will be an overall test, just like there was at the end of health decisions. Okay, so we're starting with typicality. And there are these toys called pattern blocks, and I wish that we were all meeting in person in a classroom, and I would give you my bucket of pattern blocks and you could play with them. But there's 4 kinds that we play with. There's the green triangles. If you put 2 of them next to each other, they turn into a blue diamond or parallelogram. If you had 3 green triangles, you could make a red trapezoid. They're the same size. And lastly, if you put 6 green triangles together like a pizza, then you get a yellow hexagon. And they're useful in elementary school to measure things like multiplication and division and things like that. They can also be used to talk about fractions. So anyway, we're just using them to talk about typicality. If I weigh 1 green triangle, then it weighs 1.5 grams. So what does it mean to say that this group of blocks has a typical weight? What would your suggestion for a typical weight of a block in that group be?
Wouldn't it just be 1.5 times all, like the triangles?
We could do that. So let me grab this and move it to the whiteboard. I think I know where you're going, but just so I'm not jumping to conclusions. So I'm going to take the aren't green triangles and chop them up into green triangles.
Yeah.
Pardon my lousy artwork. And then I'm going to count how many green triangles there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, what's my next step?
Uh, 17 times 1.5.
Okay. So 25.5 grams. So the total weight of everything on the scale is 25.5. That still doesn't quite tell me what a typical block in this collection weighs.
I guess.
No, Gildar, you are not part of this.
I'm not sure.
So there's 3 reasonable answers. This is something we're looking at because the word typical doesn't have only one English definition. Let me write our question at the top. What does I'm going to put that sort of in a cloud so we know it's not part of our collection. So one line of argument that's perfectly valid is to say the most common block in this collection is the blue. We have a lot more blues than we do greens or reds. So blues will be typical. And if we just say that blue is typical, then a typical one weighs 3, twice 1.5. Somebody else might say, I don't like that line of reasoning. I'm not going to take only the thing that's the most common, but I think I still agree with you. This second person might say, I think blue is typical also, but I am thinking that it's common enough to be representative of what's there. And the greens are just not enough. And the reds, there's just not enough. It would be like living in a neighborhood with a bunch of normal houses and one giant mansion and saying the mansion was typical of the neighborhood. No, it doesn't happen often enough to represent what's happening. That would work too. And that second person would also think that a blue block that weighs 3 is typical, but for different reasons. A third person would do what you were halfway through doing and say, I've been taught in school to do this thing called an average. I'm going to add them up and then divide by how many. So I'll count them all. 1, 2, 3, 4, 5, 6, 7, 8, 9 blocks. So I'll get about 2.8. So the third person gets an answer that's a little bit less than the 3 that the first 2 people got. And I'm going to say that it's not that one of those 3 people is wrong and the other are right. They just have different attitudes about what typical means. And in different situations, all of these could be important. Whether we say, let's look at what's most common, and that's how we'll represent the group, or we'll get rid of the ones that are too uncommon, they are not representative, or whether we say, let's include everything and we'll add them up and divide by how many. Is that okay of a long-winded introduction?
Yeah, it makes sense now.
So if we were all together in the same room, then I would give you a second group of blocks, and you would actually have scales, and you could make these things and weigh them and talk about how that works and so on. But the answers are the same as before, that you could say what happens most often. You could say, let's get rid of things that don't count as representative. Or we could find the average by adding up how many and then adding up the total and dividing by how many. There's a famous saying attributed to Benjamin Disraeli, but maybe not accurately, that there are 3 kinds of lies: lies, damn lies, and statistics. And one reason we're going through this bit of vocabulary about typical is that you can certainly mislead people with statistics on purpose, but it's also true that some of these words are just kind of vague. You can be misleading even without meaning to, just because of how the words work. It's important to have careful language. So in that spirit, we're going to talk about 3 different words for average. The first one is the word mean, M-E-A-N. To find the mean of a group of numbers, you add them all up and divide by how many. We just did that. That's what most people were taught in elementary school to be the average. Most people, when they say the average, that's what they mean. And it looks at a set of numbers and it provides an answer close to what happens most often in the numbers. And it's close to what's the most representative thing, but it's trying to be more inclusive. It includes all of the objects at least a little bit, even if they don't seem to be happening as much as the more popular things or more common things or more standing. So in problem 3, we'll just practice doing this again. A little review doesn't hurt. Here's a graph with preschoolers. So this graph is saying that there is one student that weighs 34 pounds. No students weigh 35. There are 3 students that weigh 36 pounds. There are 2 students that weigh 37 pounds, and so on. Make sense?
Yes.
So we're going to find the mean. We'll add them all up and divide by how many. So this is a bunch of adding. We'll have 34 plus 36 3 times, plus 2 37s, plus a 38, plus 2 39s, plus 2 40s, and a 41. And then how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So at the end, we'll divide by 12. I'm just going to peek at the answer. 453 divided by 12. So we get about 38 pounds. If we look at our histogram, does it make sense that 38 pounds is a good representative for the sample?
Yeah.
Most people would say yes, and our eyes are very good at this. It sort of looks like there's some balance. The stuff on the right is balanced by the stuff on the left. Or another way to say it is if I made one of those old-fashioned teeter-totter balance scales, then it looks like it might balance there. So that's what this picture is saying. Where a balance scale works is the mean, this type of average. I'm going to start shrinking this down in case it helps on YouTube. So how about these objects? We have the mean is the total divided by how many. So our total is, well, we have 2 on 2, 2 plus 2. We have a 6, and we have a 10. And there's 4 blocks on the balance beam. So 16 and 4 is 20 divided by 4, which is 5. These aren't measured. I don't know if they're pounds or kilograms or what. Again, it's saying that a typical thing is 5. None of these happen to be 5, but it looks like the stuff on the left and the right balance each other out. All good so far?
Yeah.
Okay. We just dealt with a histogram, That's this type of chart. So let's talk about that a little more. A histogram is a bar chart in which each bar counts a different category of things. They could be numeric values like ages or weights or heights or test scores. When the categories at the bottom are numbered, we put them in order so it's easiest to understand what's happening. But not all categories on a histogram are numbers. You can have a histogram of how many people live in different states or different counties or different cities. You could have how many people prefer different foods or so on. So in general, these sections of a histogram at the bottom are called bins, because it's like we are counting things and putting them in a certain bucket. So each one of these little things is called a bin. As we saw with the children in the preschool class, each spot on the histogram is an actual person. We could look up which student was the second one that we counted that weighed 36 and find that student's name and say, this is, whatever, Angie or Bob's spot or something. So similarly, here's a histogram of all the test scores. One student did poorly at 48%. 3 students got in the 60s. 3 students got in the 70s. Once we got to the 80s, there were 2 in the low 80s. 2 of them got 85. 3 of them got 86, and so on. So it's important to realize that in a histogram, each little section is an actual thing we measured. Each little section is something we counted. So I can ask how many students scored between 80 and 90, how many students were in the yellow. I could count them up. Say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 students scored between 80 and 90, including 80 and 90. I could ask how many students took that test and just count all of the bar sections. This histogram has color coding, the D's and the C's and the B's and the A's, but that's not normal. Histograms aren't normally color coded. It's important to realize when we make a histogram that they are designed. The histogram that we looked at, each of these little bins was 1.7% before the next bin happens. If we used a wider thing, like a bin that was 5%, it would change the shape of the histogram drastically. Now it looks like a whole lot of students got A's and very few got B's, just because of how that shape works, as opposed to this one where it looked like most students got B's. So this is another way that people lie with statistics, often without meaning to. They might not realize that their choice of how big a bin is, how wide a group to make to separate people into, will drastically affect the shape that comes out. So at home, look at numbers 7, 8, and 9 a little and play with it. There's a word we want to use called standard deviation. It shows up a lot when you read, so you should know what this is. But we're not going to actually calculate the standard deviation, which uses annoyingly advanced math. But here's basically what it is. Here we have 4 different histograms. In the first histogram, then the students seem to be clumped. There's a left clump and a right clump. We could try and find the mean, adding them up and divide by how many, but that would be kind of foolish. There aren't any students right in the middle, so finding where it balances doesn't really make anything representative. This is a test that was kind of strange. Everyone either did well or very poorly. Almost no one got in the middle. Histogram B is even more extreme. Now, not only is the middle empty, but the very edges have the most people in them. Histogram C is a better written test. Most students got somewhere in the middle, a few did very well, and a few did rather badly. If you took the mean of this sample of students, you would get something that actually represents that class. Histogram D is kind of strange. It looks like every score is about equally representative, like the teacher didn't bother to grade it, just randomly put numbers on tests for grades. We could try and say what's a typical score on this test, but that's still not very meaningful. So this is the issue that standard deviation is trying to measure. How well are things clumped to the middle? How much does a typical score really mean that it's a score that resembles what happened in this situation? So we will say that standard deviation measures how poorly a group of numbers forms a clump in the middle. This is deviation, not in the sense of like, I'm attracted to weird things, but just different from the average. So a low standard deviation is like picture C. Most people are about average. Not very many people did very well or very poor on this test. The highest standard deviation would be like picture B. No one is average. Almost everyone is quite extremely above or below. So when you're talking about different real life situations, then you can take any group of numbers and add them up and divide by how many and get a mean. But the mean could just be completely useless if it's like picture B or A, because it doesn't actually represent that group of numbers at all. Or it could be a useful representation of what happened, like in picture C. So when you read things about this study of how to treat a disease or something, then they'll often say, this has a very low standard deviation, or this has a high standard deviation. A low standard deviation means that their measurements actually fit a pattern. A high standard deviation means we did some math and it didn't actually teach us much because nothing seemed to be behaving typically. If you want to actually find the group of the standard deviation of a group of numbers, then you can with the internet. So I'm just going to copy these and open up this web page and paste them in. And so here the standard deviation was 26.7. But what that website does, I'm not going to teach you. We don't actually want you to find out the standard deviation. Okay, so far with mean and with histograms and standard deviations.
Yes. I'm
Okay,
good.
onward. Now we'll have stuffed animals. So the median is a different kind of average, and we'll talk about why we want a different kind of average. Let's go back to that preschool classroom. The numbers started at 34 and went up to 41. So I'm going to go back to this slide, make a copy of it. Now we're going to mess things up. The preschoolers insist that their favorite stuffed animals are included in the collection of things in the room. They have weights 1, 1, and 2 pounds. So we're going to take this graph and go way over here to 1 pound and 2 pounds, and have something here that's 1 pound, something else that's 1 pound, and something else that's 2 pounds. Okay with how we're breaking this graph?
Yeah.
So this is going to mess up our mean. So the mean, the total divided by how many. Well, the old total was 453. So 453 before, 454, 455, 457. The old number of people in the room was 12, and now we have 3 more stuffed animals, so that makes 15. So we get about 30 pounds. Make that squiggly to show I am rounding. So this is dreadful. We have a situation with a huge standard deviation. And so when we find the mean, then it's at 30, right? Nothing in this room weighs 30 pounds. The preschoolers weigh a bit more than that. The stuffed animals weigh a lot less than that. So this number isn't typical of what's happening in any sense. We need a better way to describe what's typically happening in this room. So now we define the median. To find the median of a group of numbers, you sort the list of numbers, so they're listed in order, smallest to biggest, and then you pick the middle number in the list. So we're just going to find the median doing that. We had 1, 1, 2, 34, 36, another 36, another 36, a 37, another 37, a 38, a 39, a 40, a 40, and a 41. So if we go in 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 3, 4, 5, 6, one more. So the middle one is 37. So the median in this case is 37. And that actually does look like it can stand in and represent what's happening in this room. A typical thing in the room is about 37 pounds. This gets back to what we did on our very first slide. Some things just aren't happening often enough to really matter. And whatever words we used for it, we shouldn't count the greens or the reds as much as the blues. They're not as representative. When we added up everything, then that caused some problems because a few pieces of this situation were extremely off. By using the median, it doesn't matter what these numbers are. If this was a 2 or a 20 or a 25, it would be skipped over. It doesn't matter what it actually is. So the median, this process of sorting them and picking the middle, gets rid of things that are extremely small or extremely big. Similarly, if the biggest thing was the school bus that weighs 4,100 pounds, that wouldn't matter at all. We're still skipping over it. So if there is a neighborhood that has one mansion, or if there is a set of incomes in a business with one CEO or so on, and you want to not include the very biggest or the very smallest, then the median gives you a better picture of what's actually typical for the situation. Okay, I'll pause again. Any questions so far?
No.
I haven't defined a median completely. What happens if I'm trying to find the median and there's no middle number? What if I have like 1, 2, 4, 8, 12, and 16? So now if I go towards the middle, then there's sort of 4 and 8 are equally in the middle. In that case, I'm going to take the mean of those two. Since there isn't one thing that's definitely the middle, then I'll say we'll take 4 and 8 and add them together, divide by the 2 because there's 2 of them, and we'll get 6. And now I'm done. Now I have defined the median. That either there's one thing in the middle, then I just pick it, and that's the median, or I have an even number of objects in my group. There'll be 2 that are equally middle, so I add them up and divide by 2. Okay, so read about that more. Just for the sake of completeness, there's a third kind of average called the mode. And I'm only telling you this because often when you search in a textbook or online for types of averages to look for more videos or whatnot, you'll see mean, median, and mode. And the mode is simply the number that appears the most often in a group. So if I am looking at the histogram, what's the tallest bar? In this case, my mode is going to be 36 because it happens most often. This is obviously how an election works, who gets the most votes, but except for elections, there's just not really any use for the mode. So we're going to ignore it. And that's all there is for being careful about typicality. It's important that we can be careful, but it's not actually too complicated. So let's look at the kinds of homework you'll have. Can you find the mean of these 6 numbers? Can you add them up and divide by how many? Can you find the median of those 6 numbers? Remember, you have to sort them first. Your list has to start with what's smallest and go to what's biggest. Otherwise, the thing in the middle won't make any sense. Here's a histogram of the number of books different students read. And this is a case where the bins are not numbers, right? Dan isn't a number, Laura isn't a number. So what's the median number of books read? What's the mean number of books read? I did those out of order. Here's that house neighborhood thing where some houses aren't worth as much as others. What's the mean and median of those home values? Which type of average is more meaningful in that situation? Number 7 and 8, there's a shipping company. It has 7 freight containers to transport. Some of them are pretty light. One of them is huge. What's the mean and median weight? And then do some extra follow-up with number 8. Number 9 gives you an example of unintentionally lying with statistics. Some news articles make a big deal when many countries have an average temperature increase well above the global. So here's a bunch of links to stories that are saying like, look, Switzerland has twice the global rate for this. So how does having our better understanding of averages explain that having many items above average isn't surprising? And then number 10 is there was a writer's strike in 2007. And according to one report, then there were a bunch of guild writers that worked full-time and their average salary was big. According to another report, The median income of the writers from the guild was only 5,000 a year. These people were poor, and of course they needed to strike. So what's really happening here? Think about what we learned with mean and median and explain that. The random exercises that will show up on tests aren't as paragraphy as some of these. All I can really ask you to do on a test is find the mean and find the median of a group of 6 numbers. I can't randomly generate a whole story problem. So let's do some practice. Let's just do this one that's right in front of us. I'm going to pause the recording and let you work on this by yourself. And when you get an answer, let me know. And then I will resume the recording and do the work on the screen, and you can check that you got it right.
Okay, so
Let's see if you got the right answer. So for A, the mean, total divided by how many? I'm going to add them all up. I'm just going to do it on my calculator and not actually write it on the board. 84 plus 34 plus 30 plus 4 plus 22 plus 12. I got 186. Does that match what you got?
yeah.
And there's 6 numbers. So we get 31. This isn't a word problem, so I just put a box around it. I don't know if it's pounds or years or who knows what the answer is labeled. Okay, now for the median. It's not a formula, it's a process. So I need to put them in order. So 4 is the smallest, then 12, then 22, then 30, then 34, and then 84. So I'm going to find the middle, which looks like these two are kind of equally middle. So I add them up and divide by 2. And I get 26. This is a random problem. The computer, the web page randomly made these numbers. In this case, we can see the standard deviation is pretty high. There are some numbers that are quite a bit smaller than either of these average measurements. And there's some numbers that's quite a bit bigger than either of these average measurements. If I was trying to do some sort of science experiment, I might think I don't have a good experiment yet because I'm not consistently getting good results. Okay, should we do another or should we move on to the next topic?
We can move on.
Okay. So if you have the Factfulness books, then chapter 6, he talks about why histograms can cause problems, why using the wrong bins when you sort information can cause you to get the wrong conclusions. Bins might hide differences or similarities. Maybe the bins themselves measure averages, and the averages were not meaningful to start with because the standard deviation was too high. Maybe bins might only count majorities. Maybe the bins might measure something meaningless. Maybe the bins are making generalizations, or maybe only special cases are being included. So read that more if you care, but the idea is that don't think that everything is generalized and the same. Look at what are the differences between things and pay attention to how there is more variety than an average would often communicate. Okay, bell curves. So we have these histograms, and people like to take histograms and sort of put a tarp over them. They say, oh, our numbers start here and they go up and then they go down and then they go up. Whether these are histograms of test scores, or maybe the bottom axis is years and we're looking at prices of things going up and down, or whatever. We often will take a bar graph and turn it into a line graph by just sort of tracing the top of the bars. Does that make sense?
Yeah.
So when you see these pictures in the bell curve section, remember that there's actually histograms underneath, right? There's bars sort of holding up this top curve. If the curve was balanced, if the mean and the median are the same number, if most objects in this collection were average, and there's an equal number of things that are higher and lower, and the chance that you're much higher or much lower is less than slightly higher or slightly lower, that's called a normal distribution. Most groups of numbers won't be so incredibly symmetrical. They will be skewed. So sometimes there's an average, but most things are below the highest point. So that's called negatively skewed. And it's a little confusing because it might look like the peak is falling off on the positive side, but realize that if the peak is sort of a little bit to the right, that means most of the things in the sample, most of what we measured, are below the peak. So that's why it's called negative. Most things are below the most common, the most typical. If it's skewed in the other direction, that's called positively, because most things are positive of what's average. So another thing that works better if we were all together is I would collect the pattern blocks and give everyone some dice. And if you roll 2 dice again and again and again, it will make a bell curve. The most common number you would get would be 7. And a little bit more often than that, you would get an 8 or a 6, and you would almost never get a 1 or a 12. And as you kept rolling the dice, you would get something that looks like that very symmetrical type of curve we had been seeing earlier. And what happens in a classroom is that it doesn't form as nicely as I have looked here. That if I look at one student's histogram, it's not very much shaped like this balanced pattern. But once I combine all of the students together and get a big enough sample, then it will always look like this. Similarly, if one student rolled pairs of dice and added together for more than just a minute, then they would get a nice overall curve like that. But it takes a while. It takes a lot of rolling. So this is our first lesson. To make a bell curve reliably, these normal distributions are also called bell curves because they're shaped sort of like a bell. To make a bell curve requires counting a large group of things. If you roll your dice and add them up just 10 times, you probably won't get a bell curve. So random events can make a bell curve. Heights make a bell curve. Weights make a bell curve. Those are just ways that characteristics of people tend to be like this. A bunch of people are in the middle. An equal number of people are above or below that most common value. And the number of giants and dwarves are quite a bit smaller than the number of people that are slightly above or below what's most common. Other than height and weight, what natural, physical, demographic characteristics form bell curves? And I'm not going to click on this, but sometime after the lecture, click on this and See if you guess right. There aren't very many that actually do. So here are two bell curves, and I want to compare them. Let's look at what's happening here. If I've drawn these right, oops, let me get that. We're looking at two bell curves that are pretty similar populations, whatever these happen to be measuring, but one is more spread out. If I drew them right, they'd have the same area underneath, the same number of students, or weighing our pets, or counting our incomes, or whatever these are measuring. They have the same number of things being measured. They also have the same middle value. But if I was to draw what's happening under the blue one, then the number of people that are exactly typical, that fit the mean, is smaller than in the group that was measured with the pink. The pink one keeps going here. There's an additional few people that are right in the middle. And then the pink has fewer people that are way off on the side. It's not zero, there's still some people there, but there are fewer of them. Whereas for blue, there's more people that are still way out in the extreme. So this is that standard deviation term again. There's more variance from the middle. There's more standard deviation for the blue group. Okay, so there we go. The problem with bell curves that many people meet up with is that scientists like bell curves too much. Remember that there are pretty few natural demographic characteristics that form bell curves. If we had a classroom and we're actually waiting while people were brainstorming, getting those, but beyond height and weight, would take a bit of brainstorming. It's more common when you construct tests designed to sort people into bell curves, like IQ tests or college entrance exams. These tests are designed to make the bell curve happen. They can do it very well. So they make the test happen again and again and again. Most people are in the middle. A very few people get extraordinarily high scores, and a very few people get extraordinarily low scores. If that didn't happen, they change the test so that it works better next time. So IQ tests are famous for measuring not intelligence, whatever intelligence would really mean, but the thing it is that IQ tests measure. And college entrance exams sort people very well and make bell curves, but they don't reliably predict whether someone is actually ready for college and will earn a college degree. Similarly, there are socioeconomic characteristics that form a bell curve. Almost no city or town has a bell curve for the distribution of wealth or income or education or whatever. But people like bell curves. So researchers will use increasingly sloppy methods of data collection or analysis until they finally get something that looks like a bell curve, because then they think they're doing it right. They had this preconceived idea that something I measure should form a bell curve, even if it really doesn't. And remember that if you change the bin choices on your histogram, it changed the shape. We could make it earlier look like most of my students in this test were B students, or we could change the bins and make it look like most of them were A students. So you can do things like this and maybe get the shape closer to a bell curve. That would make some researchers much happier. The last thing I want to mention is the phrase grading on a curve. Strictly speaking, grading on a curve means something very specific. It means that I have a test that, like the IQ test or a college entrance exam, I've given to many people before, and I know that most people will be average, Some people will be, that look more like a curve. Some people will do better than average. Some people will do worse than average. And then before I give the test to my current crop of students, because it is so predictable, because I have given this test so many times to so many students, I will know that this score will be the C's. Then maybe between this number and this number, whatever that be, that's the B's, and above it is the A's, and there'll be some number here I know, and that's the D's, and this is the F's. So even before I give the test, I can say what score you need to get an A, or between which two scores are your B's, or so on. And almost no one at LCC does this. The classes aren't big enough to make this routine work. Just like if you roll dice and add up the total only a dozen times, you're not going to get a nice bell curve. So people that use the phrase grading on a curve at LCC are usually using that phrase inaccurately. They are not actually having this curve with predetermined grading cut points before the test happens. Usually people say, I grade on a curve, and what they mean is like they fudge things of what you really need to get a B or an A or something to try and make people happy. So just be aware of that. If you are trying to find a good instructor for a class, if your schedule is flexible enough that you could go to this class time or the other class time for your class you need, and you're wondering which instructor is best, then you could look at Rate My Professor and so on. And you can also ask them if they say, how do you grade things? And they say, oh, I grade on a curve. Ask them what they mean by that. As a final thing, people like bell curves and try and put them in books and things. And there's a subtle way that you can mess things up. So this is not actually a bell curve. It sure looks like a bell curve. It has bins. Right? So here's my bins. There's sort of 4 categories of stress level. Why isn't this a histogram? Why isn't this a bell curve? If you haven't seen it, it's very subtle. I'll give you a hint. Bell curves, remember, are, because we're sort of putting a tarp over the top of our bar chart. And each thing in the bar chart should be something we measured. There was a student named somebody that weighed 34 pounds. There was a stuffed animal that weighed 2 pounds. There was a student that scored 76 on this test. And so it's always true that what we're measuring on the up and down axis are how many fit in that bin. How many people live in that state? How many students got that score? How many animals had that weight? Whatever. So do you see it now?
Yeah.
So whoever designed this is trying to be clever and use a bell curve. And the point they're making is interesting, that a certain amount of stimulation is needed by your body, and too much you feel burnout, and too little you veg out and don't get stuff done. But performance is the wrong thing. That's not counting how many here. We need this to be some sort of how many. Oh, I can't write sideways. So we could reinvent this graph a little bit. Are we wondering how many people in my family or my town or my class have one of these 4 stress levels? Or are we wondering, just for myself, how many of the past 52 weeks would I say I am in each of these stress levels? 5 weeks here, 10 weeks here, or so on. So we can think of things that we could count and turn the up and down axis into a counting how many go in each bin. But performance doesn't sound like it's doing that. And that's the end for this one. We have our 10 exercises, and then we have our random problems. There's no random problems because I can't randomly generate bell curves. And the 10 exercises aren't really about bell curves. I give you one situation that's roughly a bell curve and ask you 10 problems about it, because carbon use is a hot topic, and in Eugene and Springfield, we're actually doing pretty well overall, and maybe your household is doing very well. So this is sort of an interesting thing to learn more about carbon footprints, since I can't really ask you questions about bell curves on a test. And that's all we have for today. We've done 2 of our topics. If we go back to that table of contents, when I see you next week, we'll really start talking about mortgages and saving for retirement. And these are much bigger, slower topics. We're not going to get 2 done in an hour. But this was the introduction stuff, where we talked about the vocabulary and the issues that is our foundation for talking about the money stuff next week. Any final questions?
No, thank you.
You're welcome. Have a good weekend.
Yeah, you too.
Now you have lots of homework you can try, except that it's sunny outside.
Yeah. Have a good
Bye.
one. Bye.